What is going on, guys? Welcome back. In this video today, we're going to go through the full data science / machine learning process to build a machine learning model that predicts people's income. So this is going to be a perfect exercise for machine learning, for beginners, and for people that are somewhat intermediate. We're going to take a data set, we're going to explore the data set, we're going to pre-process the data, we're going to train a model on the data. We're also going to do some hyperparameter tuning, and in the end, we're going to evaluate and interpret the results. So for people new to machine learning, kind of new to machine learning, somewhat intermediate, this is going to be a very good exercise, and it will require you to have some basic skills already. So you should be comfortable working with Matplotlib and Pandas. You should understand basic ideas of machine learning like classification, train test split, evaluating models and stuff like that. But this is going to be a great exercise, so let us get right into it. Alright, so the first thing we're going to do in this video today is we're going to download a data set that we can use to train and evaluate our machine learning model. And in this case, we're going to go with the adult income data set. You will find a link in the description down below to this Kaggle page. And you can see it says here that this is a good starter example for data pre-processing and machine learning practices, which is exactly what we're looking for. And when we scroll down here to the data set, you can see why this is the case. We can display all the columns here. And you will see that we do have some numerical features like the age, for example, that we can use right away, or for example here, hours per week. But most of the features here, as you can see, are categorical features that require some pre-processing. So marital status, occupation, relationship, race, gender, and stuff like that. Even our target attribute, the income, is categorical because it's split up into less or equal to 50K and above 50K. So this is actually a binary classification task that we're dealing with here. And to download this data set now, you just have to click on this button, and this will download a zip file, an archive.zip file, and inside of that you will find a data set as a CSV file. I'm going to extract it here in the working directory, and I'm going to rename it to income.csv so that we know what this is actually about. And then I'm going to start a new IPython notebook, a new Jupyter notebook. You can, of course, also work in an ordinary Python script, but as always, when we do some data science and machine learning work, it makes sense to work with notebooks because you can run individual cells. You don't have to train the model every time you run the script. Every time you change some slight thing after the model training, you don't have to retrain the model every time. So I would recommend working with a Jupyter Notebook. If you have trouble setting up Jupyter Notebook or Jupyter Lab, which I'm using here, you can check out the tutorials on my channel. But it is not too difficult. So I'm going to start here a new Jupyter Notebook. I'm going to rename it to main.ipynb. And for this video, we're going to need some packages, some external Python packages, probably well known to those of you who have been doing some data science or machine learning already. So we're going to install them using pip. We're going to need pandas. We're going to need matplotlib. We're going to need seaborn, which is also for visualization. We're going to need scikit-learn. I'm not sure if we're going to need it, but we're going to also install numpy. And let me just briefly look through my prepared code. If that's everything, I think it is. So those are very basic data science / machine learning packages in Python. We're going to install them. In my case, all of them are installed already. And then we're going to import here for the beginning pandas as PD. And maybe I should zoom in a little bit here. So import pandas as PD. And then we're going to load the CSV file into a data frame. So we're going to say df equals pd read CSV. And we're going to load the income.csv file into a data frame. And this is what it looks like now. We have age, work class. I don't know what that is exactly. Hopefully it is described here. No, I don't think so. But we're not going to use that feature. I don't think that this is too relevant. We're going to use the education. Now, the educational number is not a numerical feature, really. It's a categorical feature encoded as a number. So this is not the same as an age or a hours per week feature. This is just a numerical label for these classes here. So for these categories. Then we also have marital status, occupation, relationship, race, gender, capital gain, capital loss, native country, and the target attribute, the income, which is also categorical, as we already discussed. So our goal here will be to encode all these features in a way that is useful for our model. So instead of having education and then these individual text classes, and also instead of having them here represented by numbers, we can encode this using one hot encoding. Now for this feature, I'm not sure if that's the most reasonable way, because you do have the education on some sort of scale. It goes from low education to higher education. So it might make sense to represent it here using one feature, and the larger the number, the higher the education. But for the other features, for example, marital status or occupation, it doesn't really make sense to represent them on a numerical scale. It makes sense to one hot encode them to say that every single possible value here is its own feature, and we can set it to 0 or 1. So we're going to look at this here in a second, but we can explore some of the features here. This is always the first part of the data science process, is the exploration part, so exploring the data set. And we can do that, first of all, as we did here, by printing the data, but also by looking at individual features. So for example, we can go here to education, and we can print the value underscore counts. And then you can see what kind of education we have here. We have bachelor's, master's, we have preschool. And yeah, you can see here they're sorted by frequency, not by importance, or not by height, or what do you say? So not by the power of the degree, but by how many times it occurs. I think this is high school graduation. And you can do that for all these features. So you can say df work class, for example, value counts. And the main reason you want to do that is because sometimes you might have a class that occurs exactly one time, then you might want to drop that row because it's not that important. It's also important to see, for example, I think it is in work class and occupation, that we have, there you go, we have the same feature name. So for example, question mark here and question mark here is a different feature when we use one hot encoding. Now, one hot encoding, as I said, means taking this occupation feature, for example, and turning it into these separate features. So professional specialty, craft repair, exec managerial. We're going to turn all of those into separate columns, which are either 0 or 1, so into binary features. The problem with that is that we don't do this only for occupation. We do this, for example, also for work class. And then you have this feature and this feature, which have the same name, but are actually different features. And this is, of course, a problem because then you don't know which one you're targeting when you're using the question mark. And for that, we would use a so-called prefix when doing the one hot encoding. So you can look at these things here for relationship, for race, gender, and stuff like that. Important, because some of the features might have only two values. For example, gender has male and female. It doesn't make sense necessarily to one hot encode them, because if you look at df gender and then value counts, you can see that we only have male and female here. And because of that, it doesn't make sense to make a feature male, which is binary, and a feature female, which is binary. It makes sense to turn the gender feature itself into a binary feature. Same is true for income. It doesn't make sense to have less or equal to 50K as a column and then larger than 50K as a column. It makes sense to just turn the income feature itself into a binary feature, 0 or 1. So you could say wealthy or not wealthy, for example. But yeah, how do we actually one hot encode something? It works quite easily. You can do that with scikit-learn, but we're going to do it even simpler. We're going to do it with Pandas itself, because what you can do is you can say PD, which is Pandas, get underscore dummies, and then you can provide a column. So for example, df occupation, and then you can see that it automatically turns this into binary features. So you have the individual column values that we had before. So those here turned into binary features, and you can see every time one of these columns is going to be set to 1, all the other columns are going to be set to 0, because of course they're mutually exclusive because we only had one value before. So this would now be one hot encoded. And to add this new column here to our data frame, we would have to concatenate it. But first of all, we talked about the prefix, so we have a question mark here. To add a prefix to this, what we do is we say get dummies and then add underscore prefix like this. And we can add, for example, in this case, occupation underscore. And then you would see that all these column names are now as before, but with a prefix occupation underscore. And to add this now to the data frame, we would say df equals pd concat, so concatenation. And we want to take the data frame that we had before. Actually, we need to put this in a list. So we concatenate data frames that are part of a list. One data frame is the one with the dummies here. This is the second one. And the first one is the data frame that we had before. But we're going to drop a column. And the column that we drop is going to be the occupation column, because we don't want to keep the occupation when we have all the separate occupations already as a binary feature in here. So we're going to drop the occupation, axis equals 1, and we're going to concatenate all this, and we're going to say axis equals 1 here as well for the concatenation. And then when we print the data frame, you can see we don't have occupation here anymore, but we do have these binary features here. And when we do this for all these columns, we will end up with a lot of features, which is fine. But yeah, you can try to play around. You can drop certain features. You can say, okay, I'm not going to one-hot encode anything. I'm going to do everything on an ordinal, with an ordinal encoder, so on a numerical scale. And you can see if you get better results with that. But we're going to go with one-hot encoding for this video today. So this now will be done for all these columns that have multiple categorical values. So occupation, we're going to do that for work class. We're going to do that for work class underscore. We're going to do that for the education. Actually, do we want to do that for the education? Because we do already have the educational number. I think the educational number is enough because, as I said, this is on a scale. So maybe we don't want to one-hot encode the educational. We don't want to one-hot encode the education. So we're just going to drop the education, actually. So df equals df drop. And we're going to drop the education column because we do already have the educational number, which is going to be our feature. Then we're going to also drop here the marital dash status underscore as a prefix here. We're going to do the same thing here for relationship. This is a little bit tedious now because we need to just type the column names here, relationship underscore. And then we're going to do the same thing here for race and for, do we have something else? I think we have one in the end, or we had one in the end, which was native country. So those are the ones that we're going to one-hot encode. So relationship, race, and native country. Race underscore native dash country underscore. All right, so we need to run this again here because we already encoded one column. What's the problem here? Occupation. Why is that? Let me just rerun this again. So reset the kernel maybe. Run all of this. And we still get the problem, data frame object has no attribute occupation. Oh, here. Oh, of course, because we're accessing this here as well. So work class here, marital status here as well, marital dash status, then relationship here. Then race here and native country. Native dash country here. This should work now. We need to rerun this again. And now we should only have these numerical features, these binary features, and the two features that we need to encode as binary features. Everything else now is everything except for income and the gender can now be used as a numerical or binary feature. So to encode those two, we're going to just say df and then gender is going to be equal to df gender, and we're going to apply here a lambda expression, lambda x. So for each value here, we're going to say 1 if x equals male and else 0. And the same will be done here for the income. 1 if x is above 50, otherwise 0. And now you can see that we have everything here being numerical. So we don't have any categorical features as far as I'm concerned, or as far as I know. So we can also look at the columns here, columns values, and you can see that those are the columns that we have now, and we do have quite a lot of them. So 92 columns here in total, and those are the columns that we're going to use for training. Now, what we can do for the purposes of visualization is we can also drop the least important columns. So we can say here, for example, first of all, let's maybe go with import seaborn as SNS, import matplotlib.pyplot as plt. We can just go ahead and plot a correlation heat map by saying plt figure, then figure size is going to be equal to 15, 10, for example, or maybe let's go with 18, 12 or something, and then SNS heat map df correlations, so df core annotation is going to be false because we have too many columns here, and the color map is going to be cool warm. So this is the correlation heat map. Now this basically says how the features are correlated, and you can see that we cannot really see too much here. So what's the problem here? Which column is that? There seems to be a column that we cannot use here. So maybe let's go ahead and just print df correlation. Which one is that? Income. Income is nan. Why is income nan? Because probably income has the same value every time, right? So let me just see here briefly what the problem with income is. This usually means that we have only one value, which is a problem. So income, yeah, it's always 0. Why is that? Oh, of course, because I'm stupid, because we need above 50K. So we need to rerun this again here, run everything from the top, and now it should work. Okay. So now in our heat map, yeah, we don't have any white rows. So those are the correlations here. And we want to see now which of the features are correlated, highly correlated, either negatively or positively correlated to the income. And we can't really see that here because we have too many features. So maybe what we can do is we can filter out all the features that are not correlated too much with income, and we can only display the correlations between income and the high correlation features. So we can go ahead and say correlations is going to be equal to df correlation, and we only care about the income correlations in absolute values, because a correlation of -1 is also very important, and a correlation of 1 is very important. Just when you get close to 0, it's insignificant. So I want to say sorted correlations is going to be equal to correlations sort underscore values. And then what we want to do is want to say number of, or maybe number calls to drop or something like that, is going to just be the integer of, let's say we drop 80% of the columns that are not, so the bottom 80% of correlations, we're going to drop them here for the sake of visualization. We're going to use all of them for training, or you could just use a reduced data set for training as well, but we're going to use all of them for training, but for the visualization, we're going to drop 80% of the features with the lowest correlation. So times length data frame columns, and then columns to drop. The actual columns to drop are going to be the sorted correlations, and we're going to use ilog to say we want to have the features up until number columns to drop, index, and then we're going to say df, let's say dropped, is going to be equal to df drop, and we're going to drop all these columns here on axis 1. So this is going to be our df dropped. We now have only 19 columns, so way less features. And we can do the same thing here. So we can go ahead and we can copy this code. We can paste it down here, and we can just replace df with df dropped. And you can see here, here we can also actually say annotation true. Maybe we should reduce the figure size. Let's say 12 and 10. That's a little bit too small. 15 and 10. Yeah, that works. So you can see now here, this is actually too large. Doesn't matter. We have the income here being correlated highly with, what is this? This is marital status. It seems like whether you're married or not has a high correlation with the income. Same is true for the relationship status husband, which is basically almost the same. Then we have here the educational level seems to be important. The age seems to be important, positively correlated. So being married is good for your income. Being older, having a higher education, obviously. The gender also seems to be important. So being a man, because a man is a 1 and a woman is a 0, being a man seems to be also beneficial, at least in terms of correlation when it comes to income. It could also be the other way around. No, income cannot cause you being male, but it doesn't necessarily mean that you get higher pay just because you're a male, but it could be correlated in some other way. You also see here capital gain seems to be important, hours per week worked, which is also expected. The more you work, probably the more you earn. Negative correlation here with never married. So if you have never been married, this is probably bad for your income, or it is at least negatively correlated. And here you have own child. This is interesting. Does own child mean that you have only... No, this is not the same as only child, right? Right. What is own child actually? Not sure what that means, but it's negatively correlated with income. Now, what we're going to see here, hopefully in the end, is that correlations between features are not the same thing as feature importances. Because what we're going to do in this video today is we're going to train a random forest classifier on this data set, and this classifier that will perform decently will have feature importances. So it will tell us how important the individual features are, and it is not always the case that the highly correlated features are the most important. So this is interesting to know, but those are the correlations here. So let us move on to the next step. We're going to train our random forest classifier. And the reason we choose a random forest classification here as a model is because the nature of this data set is very decision-like, if I may say it like that. So we don't have too many numerical features. We have a lot of binary features, so yes or no features. And these yes or no features are very similar, or this yes or no way of getting to an answer is very similar to a decision tree, because a decision tree has branches and nodes, and we have either or. So either you go left or you go right. And I think that the decision tree is the most natural way to approach this data set. And the random forest is basically just an ensemble of decision trees, which makes the random forest very powerful. So this is what we're going to use in this video today. We're going to say from scikit-learn.ensemble, we're going to import the random forest classifier. We're going to import from scikit-learn.model selection the train test split, and then from scikit-learn, or actually no, we're not going to scale anything here because, as I said, we have mostly binary features, so it doesn't really make, I guess, a lot of sense to do scaling. Maybe if the results are not good, we're going to use a standard scaler. But for now, we're just going to go with the random forest classifier and a simple train test split. So we're going to say now train df and test df is going to be equal to train test split of the data frame with all the features. and a test size of 0.2. So 20% of the data is going to be used for testing. And this train test split also works with data frames, not just with NumPy arrays. So it also is able to split data frames into a training data frame, in this case with almost, or not almost, more than 39,000 rows, and a test data frame with 9,700 rows, around 9,700 rows. So this is how we're going to do this. And to actually now turn this, or to actually now train the classifier, we need to actually split this also into X and Y data. So we have the data, the features, and we have the target value. So what we're going to do is we're going to say train underscore X is equal to, and we're going to say df, or actually train df, and then drop the income column on axis 1. So drop the column income, and then we're going to say train underscore y is equal to train df income, like this. And the same can be done for the testing set. So test x and test y is going to be equal to test df dropping the income and test df income. And now what we can do is we can say forest equals random forest classifier, and we're just going to leave the default parameters. We're going to do hyperparameter tuning in a second here. But we can say now forest.fit, and we can fit it on the train X data and the train Y data. This shouldn't take too long, hopefully. There you go. And then we can evaluate it on the test data to see its performance by saying forest score, and then, come on, test X and test Y. And you can see we get 85.64% accuracy, which is quite good. So 85% of the time we're accurate in predicting whether this person is earning more or less than 50K. Now, to hopefully get even better results, we can also do hyperparameter tuning. But before we do that, I want to show you here the feature importances, which can change if you retrain a model here. But we can just say forest.feature importances, and it will give us numbers for the importances of the different features. Now, what we can do here is we can say we also want to have here the feature names. But instead of now having to look up which one is which one, we can also just go ahead and say dictionary zip. So we can zip these two lists together. So forest.feature names, forest.feature importances. We can zip them together, turn them into a dictionary, and then we can see the feature importances. And furthermore, we can also sort them. So we can actually say, let's say this is importances. And then we want to say importances is equal to key and value for key and value in sorted. And we can sort now the importances dot items. And the key is going to be equal to a lambda expression, lambda x, x1. So we sort by the value, by the importances, in reverse order. So in descending order. And then we can print the importances. And as you can see here, the most important feature seems to be, actually this is important, so we should look up what that actually means. FNLWGT, so it seems to be important. Do we have some information about that? Acknowledgements, let's see. There you go. Continuous. Okay. So those are just the values. They don't describe it really. Maybe we should Google. So this is, what was the feature called? FNLWGT. This is final weight, which is the number of units in the target population. Where is this? there you go. The weights on the current population survey files are controlled. Okay, it doesn't really tell me what this is, right? Final weight, the number of people, believes the entry. Ah, okay, so this is basically not really a feature. It just tells us how many people belong to that group. I don't know if that is... Maybe we should drop that feature, actually. Maybe because it doesn't... I don't think that this is something that we can really get for a new person. At least I don't think so. So probably we should drop that feature because before we train. So maybe let's say df equals df drop that feature, axis 1, final weight drop. Now let's rerun this again and see if we get a massively different score. No, still 84.95%, pretty good. And now let's see which one is the most important feature here. The age, the educational number, the hours worked per week. So it seems like the older you get, the higher your education, and the more you work, the higher your income is going to be. Seems reasonable. Then you can also see here, marital status is very important. And it seems like gender is still important, but not at all as important as it was in the correlation heat map. Then what else seems important? Race white. Okay, this now, the interpretation of this gender and race white is political, so I leave that up to you guys. I'm not going to comment on that, but you can see here that this is how the random forest says the features influence the results. So this is how important the individual features are. Now let's go ahead, do some hyperparameter tuning, and see if those feature importances, along with the performance, of course, change, so that we can see if this is consistent with the quote-unquote best model. So what we're going to do now is we're going to say from scikit-learn dot model selection, we're going to import grid search CV, and we're going to say now that we want to have a parameter grid. And the parameter grid is going to basically list the values that we want to have for the hyperparameters. So you can look up the scikit-learn documentation for the random forest classifier if you want to. So we can actually go and say random forest classifier here, scikit-learn ensemble. And we can see here what the parameters are, what their default values are, and what the parameters are for. And you can use all of them here for hyperparameter tuning, but what I'm going to do here is I'm just going to say for this parameter grid, we're going to have the n estimators. We're going to provide, the default value here is 100, I think, so we're going to say 50, 100, and 250. Then we're going to say max depth, so how deep can this go? We're going to limit this to 5, to 10, to 30, and to none. So no limit, which is the default, I think. Then we're going to say min samples split, so how many samples we need to split a node. Here we're going to say, I think the default is 2. Here we're going to say now 2 and 4. And then we're going to say finally max underscore features. How are they going to be determined? We're going to say here square root. I think this is the default. And we're going to say log2. All right, so those are the different combinations here of parameters. And those will actually be tested in combination. So 50 with 5 and 2 and SQRT, 50 with 5 and 2 and log2, 50 with 5 and 4 and SQRT, 50 with 5 and 4 and log2, and then 50 with 10 and 2 and so on. All these will be tried in combination. So what we're going to do is we're going to say here grid underscore search is going to be equal to grid search CV. And we're going to say the estimator that we're actually tuning is going to be a random forest classifier. And then we're going to say that the parameter grid is going to be our parameter grid. And we want to have this verbose so that we can see the progress. So verbose is going to be equal to 10. And then we're just going to say grid search fit x underscore train, y underscore train. Or actually in our case, it is train x, train y. So you can see now it tries all these combinations. So it does, it shows you the progress here, and I'm going to skip that part because it's going to take some time. And you can see here it keeps track of the score, and then the best model will be returned as a result of this hyperparameter tuning. Alright, so now the tuning is done, and to get the best result here, to get the optimal classifier, what we do is we say grid search dot best estimator underscore, and you can see that the best setting seems to be max depth of 30 and min sample split of 4. Now, theoretically, if you want to further explore this, you can see here, let's just close this here, you can see that the max depth of 30 is the maximum value that we have besides none. So we could also explore maybe 50 or 60 or something like that. And the same is true for, where is it? Min sample split 4, maybe 6, 8, 10 or something like that is even better. So if you want to, you can also further explore that. But let's go ahead now and see what the accuracy is with this one. Grid search, best estimator is going to be the forest. So forest is equal to grid search best estimator. And then let's do forest dot score test X and test Y. We get 86.12%, which is very good. And now what we can do is we can look at the feature importances to see, or actually we can rerun this code here. Let me just copy this again. There you go. And the importances now are still age, educational number, capital gain, marital status, hours per week. So it seems like hours per week is now less important with this better model, quote unquote, for whatever reason. And yeah, actually it seems also like, yeah, race white is less important for this one, and gender is still about the same. Not in family, own child, wife seems to also be somewhat important. The least important feature of all is whether you're from Netherlands or whether you have never worked. This is interesting. Work class never worked is irrelevant, it seems, to this decision, which is interesting because if you have never worked, I think that is a good predictor for not having high income. But maybe it is because we don't have too many people that have never worked. Could that be true? Yeah, we only have 10 instances of never worked. So yeah. But this is how you can build a machine learning model that predicts people's incomes. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and